Hello class, and welcome to section 8.4, which is modeling with quadratic functions. By the end of today's lesson, you will be able to apply quadratic functions to model a few real-world situations. The first ones that we're going to talk about are area models that we can use to find the area of rectangles. We've already briefly talked about this in chapter 7 when we would talk about the area of those different rectangles. But we're going to get a little bit more in depth with it right now. So we're going to find the area model for the rectangle and then graph the function. So our rectangle right now has a length of 4x plus 7 and a width of x squared. In order to find the area, we're going to need to multiply those quantities, so 4x plus 7 and then x plus 2. This brings us back to chapter 7 where we needed to use that FOIL method in order to multiply. So we got 4x times x, which is x squared, 4x times 2, which is going to be 8x, 7 times x, which is 7x, and then 7x plus 2, which is 14. Giving us our final model equation then of 4x squared plus 15x, combine the 8x and the 7x to get 15x plus 14. So that's our model for the area of that rectangle. Now from there, we're going to go ahead and get into the graph of that function and talk about what it means. So in order to graph it, we're going to need to find our axis of symmetry first. So we're going to use that x formula, x equals negative b over 2a. So in this case, I've got x is equal to negative 15 over 2 times 4. Negative 15 divided by 8 is going to give us negative 1.875. So when we put that on the graph, we're going to round it to negative 1.9 because we can't really graph 0.875. But for the purpose of actually solving here, we want to make sure we use that full decimal. Now we're going to plug that back in. So you would plug that back in and say 4 parentheses negative 0, or negative 1.875 squared, parentheses plus 15, parentheses negative 1.875, parentheses plus 14 squared. And once you do that, you're going to get your vertex point is at negative 1.875. And then that y value ends up being 0.625. So that's going to be our vertex point. We also need to pick out the y-intercept from our equation. So we're going to pick that out, and that's going to be at 0.14. So now we're going to go ahead and graph. Right now, 0.14 is not going to fit onto my graph, and because I'm dealing with such small decimals, it's probably not going to be the easiest to use that vertex point. So you can also plug in other numbers that are closer. So for example, if I plugged in negative 1 into the spot of x, so 4 times negative 1 squared plus 15 times negative 1 plus 14, I'm going to end up with an answer of 3. I could also plug in a negative 2, and when I do that, I'm going to end up with an answer of 0. So right now I have points where my vertex is at negative 1.875, negative 0.625, so somewhere probably right in there. And then I've got a point at negative 1 and positive 3, and then a point at negative 2, 0. Now that's going to be a little bit difficult to see, so I'm going to go ahead and I'm going to plug in negative 3 as my next point over to give me a better impression of where that graph might be. And when I plug in a negative 3, I'm going to end up with a positive 5. So negative 3, positive 1, 2, 3, 4, 5. So I'm going to get a better impression then of where my graph actually goes. I'm going to go ahead and connect those points with my curved line. And I end up with a function that looks something along this line. Now, what does this function actually tell us once we put it on the graph? So remember, the x coordinates, or the x values, are what we're plugging in to figure out our side lengths. And then our answer, this equation, is giving us all the different possible areas. So we want to look into what would be actually plausible here. So we've got our curve, which part of the graph is actually going to tell us useful information. In this case, as you are getting bigger here, once you hit this x-axis, this right here represents an area of 0. So it's saying all of the things that you can plug in, and then your area will equal 0. So if I plugged in -2, the area of my rectangle would be 0. But we want something that actually has area, so we're going to want to plug in something that is going to get above that x-axis. The other thing here is length values have to be positive. So we really don't care about this left side of the graph. This right side of the graph tells us all of the values that are going to give us positive areas, are going to give us an area. So if I'm looking at this, the x values starting at -2 and getting bigger give us plausible answers. And then all of our answers for the area, so all of our f of x or our y values, are going to end up then being bigger than 0. So that's kind of looking at the domain and range of that function and what it means. Go ahead and create the area model and graph this one on your own. So once we graph, we end up with the curve for the area model. Again, if we were going to break it down, all of our areas that we want would start above that x-axis. So whatever this point is right here, which in this case, the graph makes it look like anything bigger than -1. We can plug in for those x values, and then again, our areas, our f of x's, are going to, in that case, then be bigger than 0. So we can use quadratic functions to model different area situations with rectangles. The other thing that we can do here is use it to solve these model problems. So a company is offering rectangular pools with the dimensions shown. Each of the pools has a deck with a 4 feet width. If Caroline wants to buy a 15-foot wide pool, how many square feet of yard will she use? So in order to figure out how many square feet, we need to know the area. In order to do the area, we need an area model. So the first thing I'm going to look at here is my length. So this part of the pool itself is 2x, but then we have these bonus pieces, which is the deck part, and each of those are going to be 4 feet. So this length part is going to be 4 plus 2x plus 4, which is going to give me 2x plus 8 for my length. And then width-wise, we have that x value, and again, we have the 4-foot pieces on either side, so we're going to end up with x plus 8 as our width. Going through and then completing the model then, you're going to FOIL, so you get x times x, which is, or 2x times x, which is 2x squared, 2x times 8, which is 16x, 8 times x is 8x, 8 times 8 gives us 64, giving us a final area model of 2x squared plus 24x plus 64. So this is our model area. I want you to go ahead and solve then for how many square feet you would need if the width of the pool is 15 feet. So what that means is you're going to take that 15 and you are going to plug that in for x. So we're going to do 2 times 15 squared plus 24 times 15 plus 64. And you would go ahead and plug that value into the calculator. And once you do that, you end up with an answer of 874 feet squared of area. So that is how much area she would have to have in her yard in order to install this pool. So that takes care of our rectangle formulas. The other thing we're going to look at is something called the vertical motion formula. This model formula has the equation h of t equals negative 16t squared plus v0t plus h0. So this answer here, this h of t, represents the height of an object at time t. Essentially what we're looking at here is any object that is traveling in a parabolic path. So anything that goes up and then comes down. So you might think of someone shooting a soccer ball. It goes up and then it comes down. Someone throwing a baseball, it goes up and then it comes down. So all of these things have upward motion, and then at some point they start going down. The V0 stands for the initial velocity of the object, so how fast it is moving when it starts. Some things, you might start with a velocity of, let's say, 14 feet per second. So when you're throwing a baseball, when it leaves your hand, it is already moving, so it's going to have some initial velocity. Other situations, you might not have initial velocity. So something where if you drop it, so let's say you were standing at the top, and then you drop it, so it's only the second half of that parabola that you're using. It wouldn't have any initial velocity. So there's going to be some value going in front of that initial t. And then the h0 stands for the initial height of the object. So the height or the position that you're throwing it from, dropping it from, etc. A lot of people ask where this negative 16 comes from. That is a constant. That will always be the same. It is calculated based on acceleration due to gravity. You're not going to need to know where it comes from or how it is derived. All you have to remember is that that negative 16 is the value that goes in front of t squared. So, for example, we have a diver jumps from a 30-foot platform with an initial velocity of 16 feet per second. What is the quadratic function to model the diver's path? And then what is the diver's maximum height? So here we're going to take that equation that we had. So that h of t is equal to negative 16 t squared plus initial velocity of t plus the initial height. So we're going to replace those quantities with the things that we know. So we know they're jumping from a 30-foot platform. That's your initial height. And we know that they're moving at a speed of 16 feet per second. That's your initial velocity. So your writing the equation becomes h of t is equal to negative 16 t squared plus the velocity of 16 feet times t plus the initial height of 30 feet. So that is my equation. Then it asks for the maximum point that the diver will hit. So we want that very top point. Again, that's going to be the vertex of any parabola, so it's essentially asking us to find the vertex. In order to start that, we need to find our x value. So x is equal to negative b, so negative 16, over 2 times a, which is negative 16. So our x value is going to be 0.5. Then I would plug that back into my equation, and I would plug it in, so I would get negative 16 times 0.5 squared plus 16 times 0.5 plus 30, and that value is going to end up giving me 34. So what that means then is that at maximum height, or the diver's maximum height, is 34 feet and occurs after 0.5 or half of a second. So a half a second after he jumps off the platform is when he is at his maximum height. For this final example, we're going to say LeBron shoots a jump shot with an initial velocity of 18 feet per second and an initial height of 6 feet off the court. So the ball is 6 feet off the court when he shoots. Write a function to represent the height of the ball after t seconds, and then find the maximum height of his shot. Go ahead and try this one on your own. So you've got that initial equation of negative 16t plus 16t squared plus 18t plus 6. Finding your x value, you get 0.5625. Plugging that back in, you're going to get an answer of 11.0625. So you would say the maximum height of about 11 feet occurs after about a half a second. If you have questions about this or anything else from the lesson, please let me know when you get to class.